Okay. Excellent. Okay, yeah. Hi, everyone. Yeah, so I'm doing a PhD at UNH, and I work with a lot of the nitrogen time series data that's collected in watersheds upstream of the Great Bay. And so I'm excited to share with you a little bit of the novel ways we're thinking about using time series data analysis in nitrogen cycling research. So I think it's important to focus on nitrogen that's collected within rivers and the Great Bay itself because it's a limiting nutrient, and in excess, it can stimulate growth of phytoplankton and go on to algae eelgrass, lead to eutrophication and other water quality consequences, which I'm sure we're all familiar with. Various organizations monitor nitrogen inputs to the Great Bay. The one that I'm going to be focusing on today is the Lamprey River Hydrological Observatory. And many of the same variables that are collected at the Lamprey River Hydrological Observatory are also collected at buoy stations in Great Bay. And this is cool because it presents opportunities to use both of these data sets to understand how nitrogen inputs from the landscape are influencing nitrogen dynamics in the Great Bay. So these data sets of inputs and outputs are useful for understanding how rain, rivers, runoff, and internal cycling of nitrogen are influencing Great Bay's water quality. And we usually explore these dynamics by treating the watershed as a black box. But it's important to remember that within the black box is a watershed that is extremely complex. It can filter, it can transform, it can retain nitrogen, and this happens across space and time. And because of this complexity, rarely is the relationships between inputs of nitrogen and outputs of nitrogen linear, and instead occurs at some time lag. And so with so much data at our fingertips across time and space, we need statistical methods that can identify what these time lags are so that we can start to meaningfully relate time series of inputs and outputs in our watershed. So we've been playing around with information theory. This is a statistical approach that incorporates time lags and can deal with data gaps, which is ideal for hydrobiogeochemical data. So information theory leverages the inherent amount of information contained within a time series. So this is based on probability distribution. So if you think about a time series that is extremely variable, it has a lot more information in it than a time series that has one type of value. So what we do is we apply this algorithm to two related time series and can kind of understand how much information is stored within a variable, shared, and then transferred. So I'm going to provide an example of how we're using this approach for understanding nitrogen transit times in the Lamprey River watershed. So, and whether this is driven by timescales that are more relevant to hydrology or biogeochemistry. And so what we do is we take the long-term record of our rain nitrogen coming in and our river nitrogen leaving within the Lamprey River watershed. And we combine these time series to reflect different probable nitrogen cycling that's happening. And we actually shift our time series by lag. So we increase the amount of time between inputs and outputs, and we apply the information transfer algorithm at each of those time steps. And from doing this, we can figure out at what lag we actually have the most amount of shared or related information between our time series. So for example, if we increase our lag from 1 to 3 weeks, we might see an increase in information transfer, but that increase from 3 to 6, we might see a decrease. So that 3-week lag time could potentially be a hotspot of how these two time series are related. I'm not going to go into the details of our paper, but I just put it here if you're interested in learning more. But I think one of the relevant sort of results that we found was that it takes about, on average, 12 to 21 weeks for nitrogen that's deposited in rain to move through the entire Lamprey River watershed and ultimately end up at the mouth of the Lamprey River. And inputs of nitrogen via rain underwent biogeochemical transformations before entering the river and ultimately Great Bay. So using this approach, we can start to create a conceptual model for how nitrogen moves in our watershed, what transformations are occurring through time, which has implications for the type and at what time scale nitrogen is entering the Great Bay. So one of the cool things we can do is now use these results to investigate our system further. So for example, one of our other results is that we found our system has memory. So it has memory of a precipitation event up to 4 weeks after it occurred. So that if precipitation happened at week 0, we can still see the effect of that precip 4 weeks later. And this is an important result to think about in terms of Great Bay ecology. So for example, what about the lag time between a storm event and Great Bay water levels, the lag time that then occurs for nitrogen loading and chlorophyll A levels? Does the same lag time and memory apply as its watersheds? We can use information theory or other time series that incorporate lag times to address this type of ecosystem scale question. Thank you.